Good morning. Through this video, I would like to explain how can we measure the dielectric constant for the various material. What is dielectrics? Dielectric is nothing but an electrically insulating material. It can be polarized by applying the electric field. Dielectrics are used to increase the charge storage capacity there in the capacitance. Here in this experiment we are going to find the dielectric constant of different dielectric material. What is dielectric constant? Dielectric constant is nothing but a ratio between the permeability of the material to the permeability of a free space. Epsilon R is equal to epsilon divided by epsilon naught. So in order to measure or calculate the dielectric constant, we have an instrument which is made by SES Instrument Private Limited. This is nothing but actually a capacitance meter. Through this capacitance meter, one can able to measure the capacitance of a capacitor. Why should we measure the capacitance of a capacitor? How it is related with the dielectric constant? Let's see this formula. So probably in your lower classes you might have studied when you are placing the dielectric material between the two parallel plates, the capacitance will be increased, and I have modified the formula here. So epsilon R is nothing but a dielectric constant which is equal to C, that is nothing but a capacitance, and D is nothing but a thickness of the sample divided by epsilon naught, it's nothing but a permeability of free space, and into area of the sample. So here, if you could measure the capacitance value C, means you can able to find the dielectric constant. A good dielectric material have very good dielectric constant. So by calculating the dielectric constant value, one can categorize the dielectric material as good or which one be a useful one. Likewise we can do. Let's see how can we measure the capacitance by using this instrument, and thereby we are going to calculate the dielectric constant. So this is nothing but a capacitance meter. Here you can see the capacitance value on this screen, and below the screen you have a zero adjustment knob. So before starting this experiment, I'm going to calibrate the instrument by pressing this zero adjustment knob, and here you have two sample holder. So this is one sample holder and this is another one sample holder. You can use whichever you need. So this sample holder is for the sample whose size is bigger, and this is actually a sample holder which can be used for the sample whose diameter is small. Fine. On the back side of this instrument, we are getting two knobs from these two sample holder. Which sample holder you are using, and that knob can be connected in this port. Fine. So now in this video lecture I am going to measure the dielectric constant of glass. So this is nothing but a ordinary glass, and this is nothing but a backlight which is used to fabricate the switchboard and other things. And the third sample holder is nothing but barium titanate. So this is actually a barium titanate sample. We are going to measure the dielectric constant of these three material by measuring the capacitance value. Now first I would like to take the capacitance value of these two samples, because it's whose dimension is almost the same, and the dimension is bigger, so I am going to use the bigger sample holder. So just I am connecting this knob, okay. So now you can see the capacitance value. Now I am going to do the zero adjustment here. So just press and wait. So the capacitance value becomes 0. Now what I am going to do means I am going to place the sample in between the two parallel plate capacitor. I have taken a glass sample and just I have placed in between the two parallel plate. You know that air is also a dielectric material. So in order to reduce the air gap, just I am screwing, and so that the plates can placed over on the sample. Now just take this capacitance value. For glass it's about 56.42 picofarad. So I'm going to note down here in this tabular column. So it's already filled tabular column. For him, the capacitance value comes near around 63.43 picofarad. And now I'm going to replace the glass sample with the backlight. So once again I'm going to screw up, and for backlight it's about 50.48 picofarad. Yes, it's 53.20, and I'm going to replace the sample with this barium titanate. Since the sample diameter is very small, I'm not able to use this bigger sample holder, so I'm going to change the knob on the back side. Just I'm inserting the knob which is coming out from the small sample holder. For this, once again I'm going to do the zero calibration by pressing this. Yes, so it comes to 0. Now I am going to place this barium titanate sample in a careful manner. And the capacitance value of the barium titanate inserted sample is around 457.43 picofarad. So just I have noted down all the readings here, and I am going to use the formula epsilon R is equal to CD divided by epsilon naught A. Here D is nothing but thickness, and A is nothing but area of the sample. We have in our laboratory, we have only these three dielectric samples, so whose value is constant actually. Here you can see the diameter value of the big plates or the small plates. So just substitute the value here and substitute the capacitance value. Don't forget here we got the capacitance value in picofarad unit. So for pico into 10 to the power of minus 12, just substitute the C, D, A value, and epsilon naught is a constant value. So substitute that value 8.8 into 10 to the power of minus 12, and if you could reduce the equation means probably you will get the dielectric constant of glass, backlight, and barium titanate. That's all.